Trauner's synthesis of Loline. And so that is this molecule here in the Loline family of alkaloids. And Trauner synthesis was I think kind of a landmark synthesis for this particularly family of alkaloids, because if you see this molecule here, at first glance it doesn't look too complicated. It's just a simple bicyclic ring structure with this second fused cyclic ring here. And it's deceptively simple. It's like the tropane alkaloids. They look simple, but the actual synthesis can be quite daunting. And previously, before Trauner synthesis, I think the last synthesis was 20 steps and was racemic at the end. So let's just jump right in and see what it looks like. So another way to write Loline is to write it as its flat two-dimensional structure here, as opposed to this three-dimensional structure. And this gives you a little perspective on kind of what you're going for. So Trauner decided to start from this prochiral alcohol here, using sharpless epoxidation to install his first two chiral centers. And this is kind of showcases the power of sharpless chemistry in general. We went from this achiral molecule to installing 2 out of our total 4 stereocenters in one step, with a 99% enantiomeric excess. So to install the rest of the carbons needed for the synthesis, he attacked this epoxide with an amine, and then protected it with a CBZ group. So another organometallic reaction, the Grubbs reaction, ring closing metathesis, in this case using the second generation Grubbs catalyst, he managed to make this 8-membered ring in 86% yield. It's pretty good. And after this, kind of a strange step, if you see, he's using thionyl chloride with triethylamine as a base, and making this cyclic sulfite structure here. So I've never seen thionyl chloride used in this particular way, but it actually serves this reaction well. And you'll see that particularly in the next step, where lithium azide is used to install this group here, and that'll be our nitrogen atom that is here on this part of the Loline molecule. So why is this step selective? And the best way to look at this is to examine the mechanism, of course. And so if you redraw this structure as its three-dimensional conformer, you'll see that this part here, this oxygen, which corresponds to this oxygen on the ring, is more sterically hindered than this one. And if you think about why it's more sterically hindered, well, if you remember to your introductory chemistry courses, the azide molecule needs to attack 107 degrees to this oxygen molecule here, which means it would need to attack from basically where this carbamate protecting group is sitting. So it's very sterically hindered, and not likely to occur whenever you consider that right next to that group we have a very sterically unhindered carbon ready for attack right here, and we can just attack from this side at the proper angle and selectively get installation of our azide group in the proper stereochemistry, and overall 83% yield, which is pretty good, all things considered. So the next step is also kind of a shocking reaction, and if at first glance you don't see exactly what's going on here, and again, the best thing to do is look at the mechanism. And so in their paper, in Trauner's paper, they proposed the mechanism to this reaction with good evidence. And if you redraw this molecule as its three-dimensional conformer like previously, and then you brominate with molecular bromine, this alkene here, you'll see that this nitrogen atom is really kind of poised to attack this cyclobrominium ion here. So in their paper, if you read the paper that I linked over here, you can see that that they took an X-ray crystal structure of a molecule, this molecule, but with oxygen protected by some sulfate group, and they found that the distance between this nitrogen and this carbon atom was only 3 angstroms. So even on the molecular scale, that's in a reaching distance, I guess you'd say. And so this nitrogen atom can easily displace this brominium ion and end up here with the ring closed, and then methanol to remove the carbamate protecting group, giving us this product C. So after this, to get the correct stereochemistry on product C, they just treated it with lithium chloride and then basified to give the free amine with sodium hydroxide. After this, the ether bridge, the final part here, if you look here on this particular drawing, it's this bridge, or this bridge. They used potassium carbonate, so they used basic conditions and microwave irradiation for energy, and installed this bridge in a total of 91% yield, which is pretty good, all things considered. One interesting thing about this step is that these things look rather far away on the two-dimensional drawing, but if you draw this puckered conformation, you just imagine you have this conformation here, but without this attached. They're actually pretty close, and it makes the reaction feasible. After this, simple reduction of the azide by hydrogen and palladium on carbon, and then sequestering it with Bach anhydride, and then a lithium aluminum hydride reduction to Loline. So I'm not sure why they chose to use this particular step here. They could have just used the Staudinger reaction with triphenylphosphine and water, heating it up a little bit and getting the free amine here. But overall, pretty good reaction, and pretty good yields, and a good example of linear synthesis as opposed to convergent synthesis. You'll see often in small molecules like Loline that they'll choose a linear synthesis because there's really not that many steps involved. And one interesting thing to note about this is how many steps this azide molecule survives. It survives bromination, treating with methanol. It survives lithium chloride. It survives sodium hydroxide. Survived microwave irradiation. It's kind of interesting how long that this azide lasts, so kind of makes it look like a hardy functional group. So in the end, a good synthesis by Trauner, and it'll be kind of hard to top for the next group that wants to attack this molecule.